So the title of I'm talking about something which is very different from the previous speaker. The title of the talk is how the mode 1 stress intensity factor is affected by plastic dissipation in heat at the crack tip. And we will focus on one very theoretical case of an infinite plate with a semi-infinite crack. I will explain why, but shortly speaking, it's because it's the only case where we can obtain analytical solution of the problem. So it's a work which has been done with my colleagues Nicolas Rank and with Paul Paris, invited by my university last year and the year before. So what is the motivation of the work? In fact, all of you know, of course, that when a crack is propagating, many people use thermoelasticity to estimate the stress field around the crack and to compute the stress intensity factor. So in fact, many people consider that the temperature around the crack tip is constant, not exactly because of the thermoelastic effect, but in fact, if there is crack propagation, all of you know that during the crack propagation, there is alternating plasticity in the reverse cyclic plastic zone. So it means that in fact, one significant part of this plasticity, I mean strain energy plasticity, is dissipated in heat around the crack tip. So due to this dissipation in heat, the temperature field around the crack tip is heterogeneous, and consequently there is a thermal stress field associated to the thermal expansion, because in fact around the crack tip the material tries to expand, but it cannot because of the rest of the material which is elastic. So how to quantify this effect on the temperature on the stress intensity factor is the main goal of the presentation in the theoretical case of the large plate with a large crack. So the plan of my presentation after this brief introduction is first we will see the thermomechanical problem and several assumptions to solve the problem. Then we will see the resolution of the thermal problem. The first important point is to be able to compute the temperature field around the crack tip. And the second important point is to solve the mechanical problem, I mean to compute the stress field and then to compute the stress intensity factor due to thermal stresses. And finally, we will see the conclusion and interesting prospects for future works. So in literature, many people were focused about the dissipation in heat of plasticity for very fast crack, for instance during impact loading or during quasi-static loading, but only few papers, according to me and my colleagues, are focused about what happens under cyclic loading. So for instance, my colleague Nicolas Rank proposed in 2008 that based on experiments that the dissipated power per unit length of the crack front is proportional to the radius of the reverse cyclic plastic zone to the power 2, and proportional also to the loading frequency. I will come back at the end in the prospects, but the proportionality with the loading frequency is interesting for future works, I think. So, for instance, if you are in plane stress, but it's the same in plane strain conditions, you can compute the reverse cyclic plastic zone with a very simple approximation, and in this case, you can see that the heat source or the flux of the temperature is proportional to delta K to the power 4. So it's important to note these two proportionality, and also that Q0, this factor, is strongly dependent on the material properties, because you see that the yield stress appears here with the power 4. But in literature, there are only few quantitative estimations of this dissipated energy. We will come back at the end of the presentation. Anyway, it's clear that there is dissipated energy, and now we will focus on how to estimate its effect on the stress field and on the stress intensity factor. So the assumption of the presentation to be able to solve analytically the problem is the following. We consider that the reverse cyclic plastic zone is small compared to the size of the specimen, and in this case the reverse cyclic plastic zone can be modeled by a light heat source. It means a local heat source. In this case, analytical solution exists. We will see it's not very difficult. And we consider that the crack is moving very slowly because in the case of the thermomechanical problem, there is a competition between the speed of the crack and the speed of the heat conduction. So up to now we solved in this case. We assume that there is no heat loss except conduction. We will come back to the assumption at the end. And we assume that outside the reverse cyclic plastic zone, the material is thermoelastic. Of course, it's an approximation, but it's enough to see quantitatively the effect. So the problem we have to solve with the cyclic loading for the crack propagation is the following. There is a mechanical problem, the usual problem that all of you know, plus the thermal problem with the heat source at the crack tip, which creates heat stress field and which will affect the stress intensity factor. I will call in the presentation K-temp, the temperature effect on the stress intensity factor. What are the boundary conditions? And the first important point, the assumption in order to be able to compute the temperature variation field around the crack tip. So with a thermal point of view, the problem is axis symmetric, and the heat source is considered as static or motionless. And we will see that in the equation, the temperature field and the stress intensity factor due to temperature is proportional to the heat source. So we have solved all for the computation with a unit heat flux. But we will see the effect at the end if we consider another value. We consider the transient regime. It means that when the crack will start to propagate, what's happened and how the heatings appear. And for the temperature effect, in first approximation, we consider that the crack do not affect the temperature field. This is a strong approximation maybe, but for future work in finite element analysis, we can take into account the effect of the crack on the temperature field. So if we write the heat transfer equation, we have this equation with the local heat source, with the Dirac function here. And we are looking for the temperature variation field with a first homogeneous temperature T0. What is the results? The results is the following. On the left, you have here from the crack tip, so the crack is here. You have the effect of the temperature, so I'm sorry for the scale, which is in small letter. Here you have 0.03 degree Kelvin versus the radius. So here there is the specimens. So the analytical solution of the temperature is the following. In fact, with the exponential integral, which is this integral, you can note that the temperature variation field is proportional to Q. That's why we have plotted all the figure with a unit flux, here 1, and with lambda, which is the conductivity, and A is the diffusivity. So what is important to see? We see that with the line heat source in our model, there is a singularity in temperature, like in stress, because of the local or punctual heat source. But in fact, we have shown in last year with my colleagues that if we do not model with a local heat source, but with a uniform heat source in the reverse cyclic plastic zone, numerically we obtain the red curve here. So the scale here you have a 5 micrometer. This example is for a very small reverse cyclic plastic zone with a radius of 4 micrometers. And in this case, we can see that outside the reverse cyclic plastic zone, there is a very good correlation between the analytical solution of the line heat source and the uniform heat source with numerical solution. So for the rest of the presentation, we can consider that outside the reverse plastic zone, the line heat source assumption is good. Now, if we want to solve the mechanical problem due to temperature, so I mean to compute the effect of this temperature field on the stress, we have separated the problem in two cases. The first case, where there is the distribution of the stress due to temperature with no crack, and then with the green function, we will compute with this stress field due to temperature what is the effect on the stress intensity factor in the other case. So what are the assumptions to solve this? And the boundary conditions. The boundary condition is a key point in this problem. So as previously, everything is computed for a unit flux. We consider an infinite plate with the following boundary conditions. far from the crack, all the stress are equal to 0. It's the assumption of infinite plate. And inside the reverse plastic zone, due to the reverse cyclic plasticity, the mean stress goes to 0. So we consider that at the frontier between the reverse cyclic plastic zone and the elastic field of the material, the mean stress is equal to 0. So it's the other important boundary conditions. And then we write the equilibrium equation. So in this case, it's an axisymmetric problem, so there is only this equation, scalar equation, and outside the reverse cyclic plastic zone, thermoelasticity with isotropic behavior. And we obtain the following results. The first, the radial stress. In fact, it's not important for the effect on the stress intensity factor because the radial stress do not open the crack. The next slide will be about the sigma theta, the circumferential stress. But this equation, this result is interesting. First, you can see here the analytical results where the stress is proportional to Q, so to the heat source. So all this curve is computed for a small radius of the reverse cyclic plastic zone for 4 micrometer and typical value for steels. We can see that the radial stress close to the crack tip is here at 0. The radial stress is negative because of the heating which try to expand the material. And you can see also that there is an evolution of the radial stress with time because of heat conduction. If we zoom on this peak, we zoom here, the scale here is meter and now we are in micrometer. You can see that there is a peak which is moving a little bit with time. The values are very small, always because we have a unit free Higgs. Here we have minus 0.02 megapascal. Now, if we look at the circumferential stress, we can see approximately the same analytical equation with some difference with the sign, but these differences are important due to the following consequence. The crack tip is always here. You can see that the circumferential stress is negative around the crack tip, and after there is a small peak in tension for equilibrium, and then it goes to 0 because of the very large scale of the material in this case. If we focus in this area near the crack tip, we see that there is a finite value around 4 micrometers, because 4 micrometers is the radius of the reverse cyclic plastic zone, which is here. So in this case, we have this stress field. Now, with this stress field, we can include in the stress intensity factor calculation and see what's happened. So the stress intensity factor has been calculated with the green function in the case of the semi-infinite crack in an infinite plate, with the temperature, the thermal stresses due to the heat source. It's interesting in this case that we obtain an analytical solution. Of course, numerically, with finite element analysis, we can solve, but here it's interesting to see the tendency and what are the important parameters. So in this analytical solution, where the f function is an hypergeometric function, we can see that Q here is a key parameter, and the lambda also is an important parameter. This equation is also interesting because it has been solved in two cases, in plane stress and in plane strain. So it's interesting for estimating what happens in the two cases. If we plot this versus time, we can see the following curve. The stress intensity factor due to temperature effect is negative. It's negative because in fact there is compressive residual, not compressive thermal stresses. It's interesting also to note that if we compare the different size of the reverse cyclic plastic zone, one magnitude order here between the two curves, the difference is very, very small. It can be negligible. And in our case, there is no stable value of the versus time. It's only an artifact about our problem, because in fact we have no heat loss, no convection, no radiation loss, and we consider an infinite plate. So in this case, there is no stable heat equilibrium. Of course, with finite element analysis, it's possible to solve a finite specimen and to include the heat loss. Here, in the case of a unit source, heat source, we can see that after 1000 seconds, the effect on the stress intensity factor is around -4, 10 to the power -3 megapascals per root meter. So, in conclusion, we can say that the temperature effect on the stress intensity factor in mode 1 is time dependent, but if you come back to the curve, after the beginning of the cyclic loading, we can see that the characteristic time here is 200, 400 seconds. If you compare to a cyclic loading at 1 Hz or 10 Hz, we can consider that during one cycle, the effect on temperature is negligible, because the characteristic time of heat conduction is very big compared to the loading period. The other point is that due to the compressive thermal stresses, the stress intensity factor under cyclic loading has to be corrected by a factor, and then consequently, if you look at the value of Kmax and Kmin, the minimum and the maximum value over one cycle has affected. There is a changement. And then, in fact, if we consider the heat effect at the crack tip, the local R ratio is not equal to the common value. It has to be corrected by this K1 factor because of the additivity here. It's different to the K1 due to cyclic loading usually computed. So, of course, the key point is what is the effect quantitatively, because now we have solved analytically the problem. If we consider a high-strength steel, Nicolas Rank has shown that the energy dissipated per cycle, here it's per loading cycle. This energy is around 10 to the power -4 multiplied by delta K power 4. And this is for a high-strength steel. If you include this value, for instance, when the stress intensity factor range is 20 Pascal square root meter at 30 Hz, don't forget that all the results are proportional to the loading frequency. In this case, the effect on the stress intensity factor due to temperature is around 2 megapascal square root meter, approximately a factor 10. Yeah. Of course, here we can see that this is maybe not negligible, and the key parameter of all this is, of course, the heat source. And this heat source cannot be computed up to now, we have to measure it. So it means that to quantitatively estimate if this is important or not, we have to carry out infrared measurement and calorimetric measurement to precisely quantify Q. Now we are doing these experiments. We have started 2 months ago, approximately, for instance, for a 2024 aluminium alloy specimen at 10 Hz, this factor is around 25 watts per meter. So you can assess approximately what is the effect, but it's very depending on the size of the specimen, because it's very depending on the thermal boundary conditions. And we have also to solve the problem in the case of a finite size, including all the heat loss, which are very important. But I think that considering the thermal effect on K is important if we want, for instance, to revisit many experimental data, for instance, about the frequency effect, maybe about what's happened in air and what happens in vacuum, because when you are in vacuum there is no convection loss, and maybe other interesting things like that. Thank you for your attention.
Questions, comments?
Yes.
So if I well understood now, if you go to with your calculations to 3000 Hz as a frequency, then you should have 200 MPa per meter shielding effect due to temperature.
There is a very big problem, according to me and Nicolas Rank and Paul Paris, for gigacycle static test at ultrasonic frequency, according to this model. But I think that an important point also is, as it's written here, is Q. I don't know what is the Q value, for instance, when you are at very high strain rate, because I guess that the mechanical cyclic behavior of the material, for instance, if there is viscoplasticity, will affect the value of Q. Usually we estimate this value by experiments with classic frequency between 1 and 100 Hz. But I don't know if you multiply by 100 frequency what's happening. But it's very important.
I'm somewhat surprised about the large value, because I have tried to use this effect to measure the plastic works, yes? Even at the threshold value. And we have performed experiments with 20 kilohertz in order to measure the plastic work near the threshold. That would be the idea, to see what happens. And the increase in that we had very carefully measured in millikelvins, yes, and we had only few millikelvins, and other effects like also this thermal effects, thermoelastic effects, because you have they cause also in this higher ratio a certain irreversibility, because different grains get different elastic stresses and therefore different heating and cooling, and therefore you have a certain loss. This also makes a heating, and you make a magnetic material, the prop walls, the movement also make heating. But these are really small. They are always even at 20 kilohertz in the near threshold region was so small that we could not really
I understand what you mean there. I see. In what you say, there are two important things, if I correctly understood, but you can correct me. The first thing is that it's clear that we have no board here, but in fact, if you look at the temperature versus time is a curve which is with a sort of, there is a thermoelastic effect at high frequency, the loading frequency, and there is a monotonous constant increase.
Yes.
Okay? So in my talk, we are only talking
about the
monotonic.
Yes.
Okay? And this monotonic increasing of the temperature, according to the few experiments we carry out, we tested an aluminium alloy 2024, a C40 steel, and a titanium alloy. This monotonic increasing is very depending on the material. If you look at the aluminium alloy we tested, the increasing of temperature is very, very small.
Yeah, because it
if
conductivity.
Yes. If you look at the steel, there is a significant heating. And the people carry on ultrasonic fatigue test knows that for ductile steel, the heating is important. For aluminium alloy, the self-heating is very small. But if we look at that, I think that, of course, maybe many things are in this parameter, but up to now, we don't know how to estimate its value without experiments. And about the experiments, you say that it's difficult to measure the strain energy, the plastic strain energy. I think we have to discuss, because according to me, you do not measure the plastic strain energy. What we can measure with infrared measurement is only the temperature, and we can compute.
Yes,
the
can compute.
You need a model to estimate the strain energy, plastic strain energy. And I think in this model,
absolutely correct. Yeah.
But in my model here, there is only the physical parameter, which is Q. But it's clear that in this model, I do not say that Q is related to the plastic energy or to another phenomenon. I think after we have to go deeper in the constitutive behavior of the material.
Okay.
See.
This is more of a comment really, but it picks up on Sylvie's and Reinhold's point. The value that you gave was an applied delta K of 20 MPa root meters at 30 Hertz, and you said that gave 2 MPa root meters thermal effect. Well, you'll never do gigacycle high frequency at 20 MPa root meters, because the experiment would only last 10 seconds. So what you're going to do is come down in delta K, and if you come down to 10 MPa root meters, you've got a factor of 16, because it's
to the power of 4.
To the power of 4. So because you've got this very strong delta K to the 4th in there, I suspect you're not going to get significant effects at the kind of stress intensity factors that you run at relatively high frequency, and so probably for many practical situations the effect's going to be quite small. I'm not saying that there aren't situations where you might notice it, but I suspect
I agree with you.
If you can measure the delta K threshold at a high stress ratio, do you think it will be significantly dependent on the frequency from this point of view of the temperature?
I don't know. I don't know.
Because the threshold would be,
Yes, but in the threshold region is one problem. Yeah, I tried it. And the problem is that the work of friction due to the fracture surface contact is larger than the work of the plastic work. And that's really, so that I gave up to measure the work. It was really, it was my idea to look what really happens at the threshold. And it was not possible. For me, maybe. There are better experimentalists.
Of course, here also in the model, which is simple, in fact. The important parameter is delta K, but in reality, maybe it's delta K effective.
Yes.
But in first approximation, to carry out the model, it's enough to consider delta K. But I think we have to go deeper in experiments with very, I will say, precise measurement of delta K and delta K effective to be close to reality. We are starting only experiments for 6 months, so it's the beginning.
Any more questions, please? Okay, Stanka speaking. That concludes the morning session. Coffee break.
So I was thinking,